Robot Talk is the podcast that sits down with robot enthusiasts from around the world and asks them the questions you always wanted answered. Like, are those robots constructing a building? And how does that thing work? Hello everyone! Happy New Year! I'm your host, Claire Asher, and this week I'm finding out more about robot swarms and how taking inspiration from nature can help roboticists develop intelligent systems that are more than the sum of their parts. But first, I'd like to remind you that you can send in questions for my future guests. And there are a few different ways you can do that. You can submit questions on the website at robottalk.org or on Patreon at patreon.com/Claire Asher. Or you can contact me on social media at robottalkpod. So, without further ado, it's time for me to introduce this week's guest. I recently had a fascinating discussion with Kirstin Petersen from Cornell University about how robots can work together to achieve complex behaviours. This week, I'm speaking to Kirstin Petersen, a professor at Cornell University working on robot swarms inspired by nature. Hi Kirstin, great to have you on the podcast.
Hi Claire, it's very nice to be here.
So you lead the Collective Embodied Intelligence Lab, which is focused on designing and coordinating teams of robots to achieve complex behaviours. So can you kind of summarise the main research areas you're working on currently?
Yes, absolutely. So it's a little more than teams. We're normally focused on swarms of robots. So that sounds a little crazy, but they do already exist. So they exist we see them in drone shows. We see them in Amazon warehouses, figuring out how to best deliver your packages to the people who will send them your way.
Sure.
And so currently in my field, we have a pretty good understanding of how to manage very large numbers of robots using like pre-planning or lots of wireless communication and then coming up with protocols. But we don't yet have a good understanding for how to coordinate, thousands or tens of thousands of robots in unpredictable environments, or when there are failures, or if the robots are so small and limited that they can't even communicate with a centralized controller. And so that's the space we operate in. And so we look to swarms in nature, ants, bees, termites, slime mold. We try to better understand what makes them so extremely resilient. And then we try to take ideas from those and then translate them back into robotics to inform sort of future robot swarms.
Mm-hmm.
So what we see when we look to nature is that, there's no high-speed communication. There's no central planning, obviously. Much more so, they rely on local communication between individuals. They rely on their own body morphology and how that lets them interact with others.
Mm-hmm.
And they leverage modifications of their shared environment to sort of coordinate information to a point where they can just sense locally and still have a good idea of what's going on. And so there are lots of ways in which we can learn from that and implement it into our robotic systems. And there are lots of different applications. So we're working on everything from smart matter, where you want it to take some shape and it takes some shape, to robots for exploration, to microscale robotics.
Amazing. So you made the distinction there between teams and swarms. Where does a team end and a swarm begin?
That's a great question. So typically when you think of a team, there are roles, right? Team has roles. There might be a leader. There might be someone who takes care of infrastructure and another person who does legwork on some particular aspect of the task. In swarms, we think of much more ubiquitous individuals, where you can start with 100 and then if you gain trust in your robotic system, you add 1,000 more and maybe 500 of them die and that's okay, and you just keep working with this sort of conglomerate of robots where you really only care about the global behavior and much less so about the particular robots.
Okay, yeah. So that's interesting because, some social insects do have like different roles, kind of division of labor within the colony. Do you have that within the swarms you're working on?
Yeah, absolutely. So, there's there's the types of robots we build for research, and then there's the type of robots that would eventually hit the market one day.
Mm-hmm.
And I think everyone agrees that the robot swarms that are eventually going to hit the market are going to have roles or hierarchies, if you will. Right? They're going to locally coordinate, and then on that scale, coordinate at a bigger structure, and maybe eventually there'll be some centralized controller.
Mm-hmm.
But right now, just building many robots and coordinating many robots and operating many robots and maintaining many robots is already hard. So we typically stick to a single kind just for now, because there's still many questions we can explore in that area.
Yeah, that makes sense. And so one area that you're working on with this that really caught my eye is robotic construction crews. And that attracted me because it's, construction with robotics is a topic I haven't really had the opportunity to talk about much on the podcast, which kind of surprises me in the sense that, like, if you'd have asked me 10 years ago, what can robots be used for? Like, construction seems like a really obvious application, and yet I find very few people actually working on this. And then on top of that, you're working on it with, swarms of robots doing the construction. So can you tell us a bit about this project?
Yeah, absolutely. So I think you're right on both accounts. First of all, the construction industry is actually one of the least digitized industries of all the industries worldwide. So it's ripe with opportunities for improvement. It is also, there's massive opportunities to improve construction, right? So it's an inherently dangerous job. You have up to 800 fatalities in the US alone annually, many more worldwide. It's getting more expensive. It's harder to construct. I think according to the UN Habitat, we have 1.6 billion people who currently lack adequate housing. There's just an immense need for housing.
Yeah.
But the whole sector is also immensely wasteful. So more than a third of all the industrial waste comes from the construction sector, and it accounts for more than 40% of the worldwide carbon emissions. So, there's a lot to do here. And on top of all of that, that's just present, right? But on top of all of that, we're also hoping to send people to Mars and the moon. And we really want to start constructing in landscapes that are really hostile for human workers. And so this is a great place for robots to sort of come in. And so works really well for a particular research profile as well, because there's lots of construction by swarms in nature. They do it really, really well. And so particularly, we're really interested by these mound building termites you see in Africa. They're little centimeter scale termites that work together in the millions to build these meter scale mounds that have very sophisticated ventilation properties. And they're just incredibly resilient. I've seen them survive all kinds of crazy, crazy environmental impacts. And so we've sort of done the same in the sense that we've shown that, at least in theory and somewhat in practice, robots don't have to have a centralized coordinator or a perfect plan on how to put a structure together. They can work like the termites. They can sort of react to what they see and coordinate through their environment to build structures in 3 dimensions that get bigger and bigger and bigger, right? So people might have heard of 3D printed houses these days, right? That's also a type of robotic construction. And those are very neat too. But they sort of have the limitation that you can't really print beyond the footprint of the printer, right? Like the gantry system is the outer shell. Yeah. Whereas here, the idea is you send out robots, right? And they just keep expanding the structure, right? There's no limit other than the amount of material you send with them. And so we're working with all kinds of stuff. We're working towards, robots that can work particularly towards blueprinted structures, like small robots that actually walk around on the structure and continue to monitor that structure after it's been built. So continue to maintain it. But we're also working with more sort of granular materials where, you can imagine you want to take a surface and turn it into a berm or a pathway that other robots can climb or a landing pad or something like that. So yeah, there's lots of fun stuff there.
Yeah, absolutely. And I mean, I immediately thought about bees and the way they construct their nests. I've read some really cool stuff about how they're so flexible in the way that they do that. Like if you give them an environment that's not what they're used to, they're kind of, they'll be like, okay, well, we'll just build it in this slightly different way to kind of still achieve their goal. But these things are, they're definitely still active areas of research in biology. So, what is it like to trying to mimic something in nature that we don't fully understand?
So that's a great point. We do have a large study on bees. So, as you say, there are many things we don't know about how social insects coordinate yet. And so we actually work very closely with biologists, and we even have some biologists in the lab to help them develop new instruments, new methodologies, new ways to analyze the data, so that they learn more and we can learn from them. And so we actually have a very large study specifically on honeybees. And what we showed there was that there are all these situations in which honeybees have a hard time constructing optimal comb because, for example, they start building in many places and that comb has to fuse together, or they build large cells and small cells for workers and drones and geometrically they don't fit. Problems like that. And it turns out even with just being constrained to local information, it's dark inside the hive, they're not all communicating. They're still able to produce near optimal solutions.
It's incredible.
And so this is immensely sophisticated process going on that we're trying to learn from. And so, 30% of my lab is just trying to, at a very fundamental level, understand what's going on in nature.
So you kind of mentioned, or we've kind of touched upon this a few times, I guess, the idea of centralized versus distributed control. And obviously, social insects. There's not one leader shouting orders at them all. So they kind of have this distributed control system where each individual is making decisions on a small scale. I feel like as humans, we're sort of instinctively drawn to a centralized control system. I guess that's what we're used to in our jobs, in our societies. And I think some people are a bit maybe unnerved by this idea of distributed control. But it sounds like that's your preferred approach.
Okay. So as I said, we're getting really good in research and industry at dealing with very large scale communication networks, right? There's a reason why you can send up 10,000 drones during a football show. And you can get really far with centralized control. So when you can, that's certainly what we should rely on, because we can make guarantees and we can reason about optimality of the system and all these good things. But at some point in our system, those assumptions are going to break, right? They're going to break because maybe there's too many individuals, right? And it's just a bottleneck trying to get all of them to communicate with a centralized controller. Could be that the environment doesn't permit long-range communication, right? Maybe you're underwater. And it could also just be because the hardware is so prone to errors that you can't really count on all the messages getting through the system. And in those cases, we're going to need distributed coordination. And so no doubt the systems that eventually hit the market are going to be, some combination of both. Something we will offload to a centralized controller, something will have distributed control. But the truth is right now, we're not very good with distributed control. And so there's a lot of fundamental research that's really interesting, at the very end of that scale, just sort of learning what we can do there. And we know from nature that it's possible, right? That it can work really, really well.
Yeah, absolutely.
So, you're right. The solutions often, when we go completely distributed, end up being a little more organic. They're a little more messy, a little less optimal for sure. But, we also find that typically they're much more resilient to failure.
Yeah, and I guess, does this go both ways in the sense that, by exploring what these distributed control systems can do in robots, you can then go back to the bees and be like, right, we understand the bees a little bit better now.
Yeah, that's always the hope, right? That some of the stuff we learn from robots can actually feed back into understanding of the biological systems. We do have an upcoming study actually on excavation by underground termites. And there we've actually specifically, some data points are easy to get, some other data points are harder to get, and we've specifically built robots to mimic the data points that are harder to get in order to learn more about the termites in that fashion. So there are definitely opportunities where it's a nice symbiotic relationship we have with the biologists.
So you're also working on soft robot swarms. What are the advantages of this approach? And what kind of applications are you imagining for these soft robot swarms?
Sure. So I'm really excited about soft robots. I've worked in the soft robotics field, and I think there's a lot that the two scientific fields can learn from each other, right? Swarm robotics and soft robots. So in soft robots, right, we're now capable of creating these really inexpensive actuators that often have built-in sensors, and they are the body of the robot, and there's a lot of multifunctionality going on. We have infinite degrees of passive freedom that are resilient to impacts, all these fantastic things, right? And they're very cheap and they're very impact resistant. But right now they're still kind of limited in what they can do. Right, unless you're willing to hook them up to a big pressure supply or to the wall with a lot of power. they can't really do much. And as soon as they can do something, it's because we've added a rigid component to them. Like we've added a camera, or we've added processors, or we've added a big battery.
Yeah.
And so they're kind of hitting the limit there. Now in swarm robotics, right, often we want mini robots, but operating mini robots and fabricating mini robots is like really, really hard because they break all the time. And they're very expensive. And so what we get from swarm robotics is we can take some very simple individuals, and by having them work together, we can achieve much more interesting, complex, emergent behaviors. And so, they can benefit from that. Like swarms of soft robots would be able to have many more of them that would be resilient, presumably work for a long time. But we can sort of achieve capabilities that are far beyond the individual soft robot. So I'm really excited about that. And again, there are like lots of examples in nature where, simple soft cells sort of come together to do more sophisticated things like, social amoeba, like slime mold, or even epithelial cells, right? Those are all examples of sort of soft systems that work well.
Yeah, slime molds are really cool. I suspect the audience won't be familiar with them. My background in evolutionary biology means I am. I don't even really know how to go about explaining slime mold.
Well, okay, so let's think about it. So you would know how many neurons do we have?
A lot.
I don't know. It's something like 6 billion neurons or something like that, right? And so the slime mold has 0 neurons, right? It's just this little amoeba. And most people are familiar with the single cell slime mold that sort of, it grows and they've seen it like grow towards oatmeal and can solve mazes and fun things like that. It's been quite popular in the media.
Yeah, they've like recreated maps of like the US with it.
Right.
Yeah.
Which is already very impressive for single cell slime mold. But in my opinion, the social slime mold is, where the magic happens, because here you have these single celled amoeba that can move around on a substrate, right, and feed. But then as soon as you start to starve them, they'll aggregate into this moving slug, right, that moves in a whole different way compared to the individuals. And eventually, if you keep starving them, that slug will turn into a fruiting body with a stalk made of dead cells and spores that fly off to repopulate new areas, right? And so you have this like immense change, like metamorphosis, and they start working together, and then some altruistically die and others fly off to populate, right? And all of that happens in a no neuron organism. It's actually amazing.
Yeah, it's incredible. I would love to see some slime mold inspired robots for sure.
There are some out there, but they don't quite look like slime mold yet. People are certainly working on it.
Yeah, incredible. So something that you mentioned right at the beginning is sticking in my mind. The idea of these kind of like shape-shifting robots, or shape-shifting robot swarms, I guess. And that just made me think of I don't know if you've seen the film Big Hero 6 with not with Baymax, but with the
swarm.
The swarm, yeah. I mean, is that obviously not for evil purposes, but is that the kind of thing that you're talking about?
Yeah, I mean, it is essentially, right? I think, that's a hard goal to set.
Yes.
but the whole concept is to say, sure, we can build a really sophisticated robot. We can throw hundreds of millions of dollars at it or pounds at it, right? And we can like throw all the bells and whistles at it, and it can do really fantastic things. But it turns out, at the opposite end of the spectrum, when you have a super, super, super simple robot, maybe a robot that even just has a single degree of freedom, single actuator, and maybe just 1 or 2 sensors, if you put enough of those together, you can achieve something equally remarkable, right? And so that's really, in my mind, where the holy grail is, right? Like, sure, we can always make things more complicated, but like it's more interesting to learn what we can do from something that's as simple as possible.
Yeah, yeah. Do you have thoughts about what you might use that kind of robot swarm for?
It's funny, all of our robots are simple, but the particular one you're referring to, this shape-shifting one, is kind of what we find that it can be used for is emergent. As in, we try things and everything we expected falls apart, right? And then we go back to the drawing board, and then suddenly we see some phenomenon that we hadn't expected, and something new comes about. And so currently we're investigating sort of entangled matter that can collectively move over surfaces and sort of collectively break when that's advantageous, and things like that.
Wow.
So, at a big scale, it looks a little silly, but the rules that we come up with and the types of mechanisms we come up with can scale to really small scale robots. And so it's really exciting.
Yeah, that's kind of mind boggling. I like it. So my background is actually in ant behaviour. So have you done anything that's been inspired by ants?
Yeah, so actually the entangled robots are inspired by fire ants. Yeah. We've also had ants in our lab, but we're not as good at keeping them alive as you guys are.
It's a challenge.
It is, as it turns out.
I always think that it would be really cool to do something around, it might be fire ants that do the thing where they bundle together and float across the water or like make bridges.
Yeah, the fire ant rafts. Yeah, absolutely. Exactly. And so there's some very smart minds at Georgia Tech that have sort of pursued that and sort of looking at them in terms of not what the individual ant does, but more like what is it? How does it work as a material almost? The blob of ants as a material. And because they're experimental physicists, they're then translating ideas to that into this kind of smart matter systems. And those are the people we're working with.
Cool. I would love to see the outcome of that research.
As would I.
Kirstin, it's been fascinating chatting to you today. I've been talking to Kirstin Petersen from Cornell University. Thank you. Thanks for listening. If you enjoy Robot Talk, I'd really appreciate it if you could share the podcast, subscribe, and leave a review. It really helps boost the podcast, so thanks in advance. And don't forget to join the Robot Talk community on Patreon if you'd like to support the podcast and get access to some awesome perks, including behind-the-scenes updates and monthly bonus episodes. Visit patreon.com/Claire Asher to find out more. Next week, I'll be chatting to Gianmarco Pisanelli from the University of Sheffield about working with robots in industry. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk is brought to you by the Hamlin Centre, Imperial College London.